Welcome you all to a new session. In this session we are going to start with programmable logic devices. In the previous sessions we have seen in the unit 1 as the basic numbers, alphanumeric codes, binary codes, gray codes and the conversion from one form to the other form. In unit 2 we have seen signed numbers representations. Then coming to combination circuits we have seen off adder, full adder, full subtractor, parallel adder, parallel subtractor. Then we have seen encoders, decoders, mux, that is multiplexers and demultiplexers, and we have seen BCD to 7 segment display, and we have seen parity bit constructor like parity bit combinational circuits, and we have seen various number of adder circuits also. Now in this session we are going to start with unit 3, that is programmable logic devices. Actually, how does these programmable logic devices are designed and what are its types, and how we are going to utilize these circuits in generating different types of codes at the output level, and how they are able to utilize to store data in them or to implement any kind of logic in them. We'll see them detailedly in this particular unit. Now, PLDs means programmable logic device. Now that's what I told you. Design of combination circuits using programmable logic devices. Means I am going to dump or the required design onto PLDs. Now there are 5 types of PLDs. Like if you observe clearly, I am having the first PLD as PROM, that is programmable read-only memory. Second one as PLA. PLA stands for programmable logic array. Third one as PAL, that is programmable array logic. Fourth one as CPLD, means complex programmable logic device or devices. Next, the last fifth one is FPGA, that is field programmable grid array. In some textbooks this grid is also written as gate array. So you find these 5 types under PLDs. Those are PROM, PLA, PAL, CPLD and FPGA. So 5 types of devices are there under PLDs. Now apart from this PLDs, what you see under unit 3 is LUTs, that is lookup tables. And the last one is we are going to write Verilog code, that is, for example, if you are having C, Java, Python. Similarly, we have HDLs. HDL stands for hardware description language. Means we are going to describe an hardware through a language. That language we call it as Verilog language. So using Verilog language we are going to write programs for gates, adders and decoders. So this is what we are going to see under unit 3. Let's begin with the basic concepts of PLD. How PLD looks like, what it differentiates these devices, how we are going to see these designs in our digital electronics, and how we are going to implement our circuits onto PLDs. We'll see everything on this particular video. Let's get on to the devices. First we'll see what is the basic difference between this is PROM, PAL, PLA. Now, before getting directly into the block diagrams, I wanted to tell you that these 3 devices, either it is PROM or PLA or PAL, these all 3 are programmable devices. Now programmable devices contains gates only. Either it contains AND gates, OR gates, XOR gates, exclusive NOR gates, NAND gates, NOR gates, everything, all the basic gates, special purpose gates, what we call universal gates, all these combinations combined we call them as PLDs. Now in few devices AND gates are programmed, in few devices OR gates are programmed, in few devices both AND gates and OR gates are programmed. So based upon that programming capability only we are differentiating our devices. You see the diagram properly. Now I am talking about PROM. This is my first device as PROM. Now PROM I am providing inputs to my fixed AND array. Means AND gates are fixed here. Means I am not able to disturb or I am not going to do any kind of programming with my AND gates. Now these AND gates are utilized or designed based upon a decoder. My decoder will be there. That decoder will be having that AND array. Now the programming part. Coming to programming is I am able to define or I am able to do the programming only on the OR gates. That I call it as OR array. Means a series of OR gates will be there. So my implementation circuit or implementing design should be programmed using these OR gates. So in PROM, AND gates are fixed, OR gates are programmable. So from OR gates I am going to generate my outputs. So from traveling from inputs, it goes through fixed AND gates, from AND gates to OR array, programmable OR array, from programmable OR arrays to outputs. Coming to PAL, programmable array logic. Here AND gates are programmable here, whereas OR gates are fixed. Means the logic or the circuit or the combination which I wanted to implement, that can be done through AND array. Here OR gates are fixed here. So my inputs will travel through programmable AND array. From there it will go to fixed OR array. From there a output will be generated. The next device is programmable logic array, PLA. Here AND gates are programmable as well as OR gates are also programmable. Means my design will be implemented on two gates, either on both on AND gate as well as OR gate. Now how to remember? There should be a small logic which are programmable, which are fixed. That should be remembered. There is a small logic which we used to remember when we were studying engineering. Now if you observe PROM, PAL, PLA. In PROM the middle the alphabet is O. O means here OR gates are programmable, AND gates are fixed. Coming to PAL, the middle alphabet is A, means AND gates are programmable, OR gates are fixed. Coming to PLA, there is nothing, no A and no O, so both are programmable. So this is how we used to remember which are programmable and which are fixed. So this is what the basic structures or the basic blocks which contains in PROM, PAL and PLA. Let's get in detail structure how we implement them using any kind of implementing design. Now PROM. PROM stands for programmable read-only memory. Programmable read-only memory, that is what we are giving fixed AND array and programmable OR array. We are getting outputs here. Now outputs we are not going to get that easily, right? Like it should contain some inputs and outputs. So it is going to have k input lines and n output lines. So k input defines the number of addresses, n outputs will define the data which is going to get generated at the output level. So my size of the ROM, what is the size of PROM, he might ask you, or else they will give you directly the size of the ROM, PROM. So the size is defined as 2 power k into n as my size of my ROM, that is read-only memory. Programmable read-only memory size will be 2 power k into n. N is number of data lines at the output level, k is the number of addresses at the input level. So this is what the size of the PROM is going to get defined. So this is most important diagram. After this block diagram, this is very, very important, as it is showcasing the number of address lines at the input level and number of data lines at the output level. We will see with an example. Now this is an example. He is telling that design a PROM which can implement a full adder circuit. Means I need to implement a full adder circuit using a PROM. Means I need to put my full adder design into a PROM which is going to exhibit the operation of full addition. Now you know this particular truth table or functionality table of full adder circuit. That is, it is going to have 3 inputs A, B, C, and it is going to generate 2 outputs. that is sum and carry. Now you know how it is getting generated, sum and carry. This we have seen already in the combinational circuits, in both in off adder, full adder, everything we have seen in combination. Now you know this table. So based upon this particular table, I am collecting all my minterms of sum as well as carry. Now sums are 1 at, I need to collect only ones, right? So I am collecting ones. So 1 is presented 1, 2, 4 and 7. So I am writing all 1, 2, 4, 7 as my minterms for my sum. Next, carry is presented 3, it is presented 5, 6, 7. So I am collecting all my minterms for carry as 3, 5, 6, 7. So I have collected minterms for sum as well as carry. Now let's see what I have to do using this particular minterms. Now this comes actual implementation of our diagram. This is full adder ABC generating sum and carry. This is a table. We got all our minterms. Now using minterms, I got my expression also. That is, this expression can also be written as A exclusive, B exclusive, C. There is one more extra symbol which you have received. We'll erase this particular thing and I will write it again. This can be written as A in exclusive with B in exclusive with C. When we simplify it, we get this expression. But we are not going to utilize this expression here. We are going to directly put this here directly. So that is sum expression and carry expression. Now you got 3 inputs. So as I told you, fixed AND gate. There I am utilizing decoder there. So 3 inputs. So 3:8 decoder I am using there. Right? That is n is to 2 power n. That is 3:2 power 3. That is 3:8. So I am marking all my outputs 0 to 7. That is 0, 0, 0, 0, 0, 1, 2, 3, 4, 5 till 7. Now I need to program only OR gates, PROM means. So I am drawing 2 lines with 2 OR gates. Why? Because I got 2 outputs, sum as well as carry. Now these things got sum got what values? 1, 2, 4, 7. So I am marking 1, 2, 4 and 7. I got my sum value as output. Next, coming to my carry. What are the values? 3, 5, 6, 7. So I am marking 3, 5, 6 and 7. I got my carry. So this is how you implement a PROM concept. Like you are programming a ROM for implementation of a full adder using a PROM structure. So this is what how you implement a programmable read-only memory for implementing a full adder circuit. Thank you one and all. We'll meet in the next session.